Good morning, everyone. My name is Rishabh and I'm from brand CSE AIM, and I'm going to talk about the topic diagonalization of a complex matrix. Diagonalization. Diagonalization in matrix is a process of transforming a square matrix into a diagonal matrix, a matrix with all of diagonal elements 0, using a change of basis formed by the matrix eigenvector. A square matrix A is diagonalizable if there exists an intervatable matrix P and a diagonal matrix D such that A is equal to P D inverse P. Here D is the diagonal matrix whose diagonal entries are the eigenvalues of A, and the columns of P are the eigenvectors corresponding to those of eigenvalues. Why diagonalize? Diagonal matrices are much easier to work with, especially for powers and exponentials. Diagonalization simplifies solving system, analyzing transformation, and computing powers like n. What are complex matrices? Complex matrix is a matrix whose entries are complex numbers, which are numbers of form A plus IB, where A and B are the real numbers and I is a square root of under minus 1 is the imaginary unit. Any matrix in which at least one element is a complex number like 2 plus 3i or 2 plus 3i or minus I is called a complex matrix. Complex matrices are written just like real matrix but use complex numbers as entries. Mathematical relevance. Linear algebra. Complex matrix broaden the set of possible eigenvalues and eigenvectors, making more system diagonalizable and solvable than would be possible with just real matrix. Complex analysis. The study of function involving complex variable often uses complex matrices, especially in transformations and mapping. Quantum mechanics. The mathematical frameworks uses complex vector spaces and matrices like Hermitian matrix because quantum states are inherently described using complex numbers. Engineering application. Single processing. Many algorithms, such as Fourier transform, deal with signals that are naturally and efficiently represented using complex numbers and matrices. Electrical engineering. AC circuits analysis relies on complex numbers for representing impedance, voltage, and current, so matrices with complex entries are common. Control system. Stability analysis of systems uses eigenvalue of complex matrices to determine system response characteristics. Vibration and structure analysis. Modes and frequencies are computed using complex matrices, especially when damping or non-conservative forces are present. Definition of eigenvalues. An eigenvalue of a square matrix A is a special scalar lambda such that when you multiply A by a non-zero vector V, the result is just V scaled by lambda. AV vector is equal to lambda V vector. Definition of eigenvector. An eigenvector is a non-zero vector V such that under the transformation of matrix A, its direction is unchanged, only its length is scaled by lambda. The vector V is the eigenvector associated with the eigenvalue. Importance of diagonalization. Spectral analysis. Diagonalization tells you the spectrum eigenvalues of a transformation, which reveals stability, dominant modes, and long-term behavior of systems like vibration, population, models, and circuits. Decouples interaction. In diagonal matrix, each variable evolves independently, so diagonalization separates complex interaction into simple individual components. Theoretical insights. Diagonalization proves key mathematical results like spectral theorem for symmetrical matrix and is crucial in quantum mechanics, physics, and engineering. What does it mean for matrix to be diagonalized? Diagonal matrix D. All entries of the main diagonal are 0. Only diagonal entries may be non-zero. Similarities transformation. Diagonalization means finding a new coordinate system, basis of eigenvectors, where the matrix acts as just stretching along axis, not rotating or mixing them up. Simplifies calculation. This basis, multiplication by A is equivalent to scaling each axis by its eigenvalue. Condition for diagonalizability. A square matrix is diagonalizable if and only if it has enough linearly independent eigenvectors to form a basis for its vector space. Main condition. An n into n matrix A is diagonalizable if and only if there are n linearly independent eigenvectors of A. Additional points. If a matrix has n distinct eigenvalues, it is always diagonalizable. But the converse is not true. Repeated eigenvalue may still allow diagonalization if the geometric multiplicity is equal to the algebraic multiplicity. Matrices with defective eigenvalues, where the algebraic multiplicity is greater than the geometric multiplicity, can be diagonalized. For real symmetric matrix and Hamilton matrix in the complex cases, diagonalization is always possible because such matrices always have enough orthogonal eigenvalue. Summary table. N distinct eigenvalues we can diagonalize. Each eigenvalue geometrical multiplicity is equal to algebraic multiplicity. Yes, we can diagonalize it. No, not enough independent eigenvalues. No, defective. Real, symmetrical or Hamilton matrix. Always yes. It can be diagonalized every time. Steps for finding diagonalizing a complex matrix. Step 1. Find the eigenvalues. Compute the characteristics polynomial. Solve for lambda eigenvalues. This can be real or complex numbers. Step 2. Find the eigenvectors. For each eigenvalue lambda I, solve A minus lambda I into identity matrix into V is equal to 0. The non-zero vectors that satisfies this equation are the eigenvectors corresponding to the lambda I. Check diagonalizability. A matrix is diagonalized if and only if it has n linearly independent eigenvectors, where n is the size of matrix. In the other words, the geometrical multiplicity, the number of independent eigenvectors for each eigenvalues must be equal to its algebraic multiplicity, repeated factors in the characteristics polynomial. Step 4. Form a matrix P. Construct a P by placing the independent eigenvectors as columns, which is also known as model matrix. Step 5. Form a diagonal matrix D. The diagonal matrix D has a corresponding eigenvalues on the diagonal. Step 6. Verify the diagonalization. Confirm that A is equal to PD inverse P or equivalently P inverse AP is equal to D. Characteristics polynomial in complex matrices. Definition. The characteristics polynomial of any square matrix A including complex matrices is defined as PA lambda is equal to det A minus lambda I, where lambda is a complex number, the interdeterminate I is the identity matrix of same size as A. This polynomial is monic. Leading coefficient is 1 and the degree is equal to the size of the matrix n. Let us discuss an example of 2 into 2 complex matrix. A is equal to 1 iota minus iota and 1. Step 1. Find eigenvalues. We have to find the characteristic equation to find eigenvalues. For that, we have to do det of A minus lambda I. After finding the characteristic equation, we have to set it to 0 and find the roots, which are lambda 1 and lambda 2. Lambda 1 is equal to 0 and lambda 2 is equal to 2, which are called as eigenvalues. After finding eigenvalue, we have to find eigenvectors with the help of eigenvalue. For lambda 1 is equal to 0, solve AV is equal to 0. By the matrix A, 1 iota minus iota 1 into matrix XY is equal to 0, 0 gives the equation after multiplication x plus iy is equal to 0. X is equal to minus iota y. Set y is equal to 1 as an arbitrary constant to get the eigenvector. We get the eigenvector as v1 is equal to minus iota 1. Lambda is equal to 2. We have to do the same thing which we did for lambda is equal to 1. A minus 2i into v is equal to 0. Minus 1 iota minus 1 into xy is equal to 0, 0 gives minus x plus iota y is equal to 0. X is equal to iota y. Set y is equal to 1 to get eigenvector v2. Iota 1, v1 and v2 are linearly independent, so A is diagonalizable. Build P and D matrices. P is also called as model matrix and D is diagonalized matrix. Place eigenvectors as columns in P in the same order as eigenvalues in D. P is equal to matrix minus iota, iota, 1, 1. D is equal to matrix 0, 0, 0, 2. For verifying the diagonalization of the matrix, we have to find the inverse of the model matrix, which is P. Compute the determinant of P. Det of P is equal to minus 2 iota by finding P inverse is equal to 1 by det P into A. So after simplifying 1 divided by minus 2 iota, multiplying the numerator and denominator by iota, we get iota by 2. Thus, the P inverse is equal to iota by 2, 1 by 2, minus iota by 2 and 1 by 2. A quick verification. Because v1 and v2 are eigenvectors with eigenvalues 0 and 2 respectively. A v1 is equal to 0 into v1. A v2 is equal to 2 into v2. Therefore, AP is equal to PD. So, P inverse AP is equal to D and A is equal to PD P inverse. Final result. A diagonalization of A is equal to PD inverse P with P is equal to minus iota, iota, 1, 1. D is equal to 0, 0, 2. P inverse is equal to iota by 2, iota by 2, minus iota by 2, 1 by 2.